Now we're going to make another new functional group called an imine. Okay, and this is with a nitrogen, which is, you can think of using an amine to make an imine. Okay, the main difference is an amine is an alkyl group with an NH group of some kind. It could be primary, secondary amine. So right now we'll focus on a primary amine, meaning one R group, and the rest are hydrogens. An imine is a carbon-nitrogen double bond. Okay, so that's our goal. And it's very similar to the reaction we just did with alcohol and water. So let's look at those reactions. When you have alcohol and water, we first had to activate the carbonyl because this is a weak base. We then had the nucleophilic attack. Then we had a proton transfer. That's usually the steps. One would be, let's write it in. We have step one. We have step one, activate the carbonyl. Step two, nucleophilic attack of our nucleophile. And step three, proton transfer as needed to get to your final neutral product. So we want to follow the same thing here, but notice that an amine itself is more basic than an alcohol. That's because nitrogen's less electronegative than oxygen, so it's more willing to share its lone pair. So it's more able to pick up this acid. I don't want so much acid that this is deactivated, because there's this possibility of a side reaction, which is that this will pick up H+, and that'll make a protonated amine, which is no longer a good nucleophile. So I definitely want to minimize that. I don't want to have a lot of acid present. I just need a little bit in order to protonate here, because this is also a basic site. So my first step is going to be this. I just want to make sure, though, that I clarify we're not in a very acidic solution. Otherwise, our nucleophile would be deactivated. All right, so let's do this. So first step is protonate to activate our carbonyl. Okay, and then can you imagine what our second step is? Our second step is going to be the addition step. So I'm going to have the nucleophile attack and get the nucleophilic addition here. So here's the OH group that was on there before, and now I've got this nitrogen with extra bonds, so it's going to be positive. Protonated amine group right here. All right, so now at this stage, can you picture what we're trying to do? Okay, we did the nucleophilic attack. Whenever you get lost in a mechanism, always look at what you're trying to do. Look for your product. My goal is to get from here to here somehow. So I want to lose the OH group, so because it's not in the product, so I don't see it here. I want to make a double bond between these guys. And I lost my hydrogen somehow, okay, because the nitrogen's neutral at the end. So I know I'm going to do some proton transfers to get rid of those. Okay, so what I will do is to lose the OH group, I need a proton transfer. Now, sometimes some books or teachers or students show the oxygen grabbing this proton. It doesn't necessarily have to grab this one. It could grab the protons floating around in solution. So I actually like to show it as that, where you have protons floating around in solution. I'll show them in a different color. Okay, so let's say my green protons. It could grab over here. It could grab over here, but I just like to show that it doesn't have to. Meanwhile, I also have other amine molecules that can take these protons away, because I need to do that as well. Now, I sort of show that all in one step, but you don't have to. You could show this protonating, then write it down, then show this getting deprotonated. But, just to make it more brief, I'm just going to show it right now as both. So let's say I have another amine group, and it comes in here. All right, so I'm doing a protonation here to make this a better leaving group, and I'm making this deprotonation here to go toward my imine, which does not have the extra hydrogens on it. All right, guys, so I think you can see this. Sorry, it's a little messy, but my water got protonated. So my hydroxyl got protonated. Now that's a good leaving group. And then I've got this here, and I want to make a double bond here and kick out the water. Can you show me the arrows that would achieve that? How can I make a double bond here and kick out the water? I think you can tell from what we did before up here that it's in this step right here, I had used a lone pair to kick that out. So that's what I'm going to do here as well. So I think it's very helpful to draw the lone pairs because sometimes they tell you what to do. All right, I'll give you some hints. Okay, so now I've got my double bonded nitrogen carbon, which is the imine, but it's protonated. So now I want to deprotonate this to get to my product. So what will I do here? I'll just use another amine and I'll deprotonate this. So NH2R group, this grabs here, deprotonates, and then I get my product, which go ahead and write it out. All right, so our product is right here. It's my imine. So there's another term for you in addition to hydrate and acetal and hemiacetal. Learn what an imine looks like. That's what this is. And then notice that the product of water is also formed. And so that comes from this water leaving. So you can either put plus water here, or oftentimes people just show minus H2O in the step where that water gets lost or eliminated. Okay, so does it make sense to you that this is not just a nucleophilic addition, but an addition-elimination reaction? Elimination referring to the water that gets eliminated, so the oxygen is no longer part of this main product. All right, usually, I don't know why it is, but students can get the hydrate and the acetal pretty well, but with the imine, I don't know why, it's just more difficult. It's exactly the same thing, but just with nitrogen. And so I don't know, that sort of makes people nervous a little bit. So what I recommend is actually you do this with all the reactions we've done so far. You've got your acyl addition reactions, nucleophilic addition. So like the stuff we did at the very beginning with the Grignard, okay, and the hydrate or hydride ion. Okay, so you do those, and the cyano, the group, okay, cyanide. So that's one thing. And then you practice your nucleophilic addition elimination. So you do the hydrate, that's over here. So you do the hydrate, do the mechanism, write it out, okay? Do that for the hemiacetal and the acetal. So write out the full mechanism, which is this whole thing. Okay, write it out, make sure it makes sense to you. And then write out your imine formation, okay, which is the same thing again, but they're all nucleophilic addition elimination. So write them all down separately, okay, and that will all go into your mechanism portfolio. And then in addition to this, I have one more I want to show you, which is what happens when you have a secondary amine instead of a primary amine. And that's this reaction right here. So here's my secondary amine, meaning it's an amine with two R groups. I've got my carbonyl group, aldehyde or ketone. I'm going to do an addition of this amine, but I'm also going to lose water again, and that's how it's going to be addition elimination. Now the functional group here is called an enamine. So not just an imine, but an enamine. What's an enamine? It's an ene, or a double bond, with an amine attached. So it's not got the pi bond here, it has it here instead. Now, how does that happen? Okay, so I hope you're wondering that, because you're going to find out in just a moment. So same kind of thing here. We have acid catalyzed reaction to protonate here, activating this as my electrophilic carbon to make the carbon more electrophilic, more positively charged. That will make this amine want to attack here. And take a look at some of the mechanisms that students have already done for us down here. So let's take a look at the mechanism for this. Here we have protonation. That looks good. So I want you to make a note of which step can be drawn differently in my view a little bit better. So step one, perfectly fine. Activation of the carbonyl. Let's talk it through, okay, for practice. Activate carbonyl. So on an exam, you can remember these steps. Oh, number 1, I have to activate the carbonyl. Okay, again, because this amine is a weak base. So activate the carbonyl. Second step looks like nucleophilic attack. That looks pretty good, right? Nothing wrong with that. Nucleophilic attack. Here, this step right here, water gets protonated, and this amino group, ammonium group gets, or protonated amine gets deprotonated. Okay, so do you see how that can work? But I mentioned previously that you could do those as separate proton transfer steps, and often they are. So it's rather than intramolecular, we usually show them differently. So for example, number 3, I'll just write proton transfers. I would probably, instead of this, not a big deal, but I would just grab an acid from solution, not from the same molecule. And then I would use the base, another amine, and I would pick up that hydrogen. So rather than having this arrow right here, okay? But you know what, if you did this, it's fine. It's just more likely that it interacts with the solution. All right, step 3, we do this leaving group leaves. Nitrogen comes in with its lone pair at the same time. That's my elimination. So sort of like an E2 elimination, okay? And then over here, I'm going to deprotonate, but there's no way to deprotonate this nitrogen and make it neutral. Do you see that? What's going on here is there's R groups, and you can't deprotonate an R group. You know, it's not a proton. So the only way to neutralize this nitrogen is to flow electrons up to it via a beta hydrogen. So this is alpha, this is beta. This beta hydrogen, just like in an E2 elimination, let's review that, E2 elimination from Chem 261. That's where you had a leaving group like a halide, okay? And you had a beta hydrogen on a carbon next door to the carbon with the leaving group, okay? And so you had a strong base, usually like hydroxide or an alkoxide, come in and eliminate like that. So this is a very similar reaction. Here's my beta hydrogen, base comes in, same base as before, my nucleophile is a base, comes in, and then this forms a pi bond, and it kicks out the pi bond to the nitrogen, neutralizing it. So that is, again, why do we have to do this? Is because, remember when we made our imine, we had a proton on the nitrogen that could be deprotonated then. But here, I have 2 R groups, so I can't just pull off an R group and flow the electrons to N. The R groups are stuck on the nitrogen, okay? So, slight modification then when you have a secondary amine. That's when you have to do this elimination with the beta hydrogen. That's why we get the pi bond here. Now, you're lucky we didn't write this mechanism out. So please, on your own, write it out on a separate sheet of paper and be able to do that from scratch. Okay, so now we're at some practice putting this all together. I think at this stage, before you do this practice, go ahead and write out your mechanisms, like I said, for all the reactions we've covered so far with the carbonyl group and a nucleophile. That includes nucleophilic addition as well as nucleophilic addition elimination. Okay, once you do that, let's take a look at these. I want you to predict what the product is going to be. And these are from a textbook by Andres Termanis, by the way. Please number these 1 through 11. We're going to draw the end product of each of these reactions. So try to figure out, am I going to make a hydrate? Am I going to do a reduction? Am I going to do an alkylation? Am I going to make an imine, an enamine, an acetal, a hemiacetal? What are these things going to be that I make? And when there's an asterisk, assume that the water is distilled or removed from the reaction, meaning usually that we drive the reaction forward, okay? And there's some more hints here at number 6. The end product is a cyclic hemiacetal, and here's some guidance for you on that. For number 9, assume ethanol is removed from the mixture to drive the reaction forward. Number 10, assume methanol is removed to drive that reaction forward. And number 11, one of the products is this molecule here. This is ethylene glycol. Okay. All right, go ahead and pause it. Okay, really do it. Pause it and try it, and then come back and we'll compare our answers. All right, guys, let's go over these and talk about some strategies for how to figure these out. Okay, so the main thing I'm looking at when I do these is the carbonyl group and the group that I'm adding as a nucleophile. So I'm picturing in my head, this is getting protonated, this is attacking here, this is leaving, this is going to turn into water, and this is going to form a double bond with here. But this is a secondary amine. So when it forms a double bond here, it's going to be positively charged. And then I have to do the beta hydrogen in order to neutralize it. Something about that enamine reaction, by the way, that I showed you, is it goes through an imine intermediate. So you can always think of it as a double bond, but if it has two R groups, you have to neutralize it by removing the beta hydrogen. That's where you make the enamine. So it goes through a protonated, or it goes through sort of an imine type intermediate. So I sort of picture that when I look at that. So what's going through my mind is I'm picturing this N coming in, and it's eventually going to replace this O because the O is going to leave as water. So I'm sort of picturing this imine intermediate, but I know I have two R groups, and so I can't just deprotonate because there's no proton here. So then I know my product's got to be a double bond here, and then this pi bond eventually flows up to the nitrogen to neutralize that. So in other words, let me show it this way. I got to have a base, the amine, come in and do that. And that's how I get this product right there. Okay? So I'm picturing the mechanism to figure this out. And after you do enough practice, you can sort of take a shortcut and not have to go through the mechanism, but just sort of visually remember, oh, there's the imine, but then it's going to turn into an enamine, and then so there's the enamine. Okay, so you might be able to walk through that on your own. All right, next one, same kind of concept. I'm picturing this nitrogen is going to replace this oxygen because in the mechanism, the nitrogen attacks the carbonyl, and then this group leaves as water. So to sort of condense all that, I sort of think of that nitrogen right here, and then that R group is going to be attached to it. So that's going to be here. So, and then do I need to make an enamine, or can I keep it as an imine? It's all up to the nitrogen. If it only has one R group, which it does, then I can deprotonate these hydrogens, and I can make that neutral just as an imine. So in this case, the pi bond is between the carbon and the nitrogen. So this is an imine as opposed to an enamine. All right, and that's because this nitrogen is primary. It's another way you can tell. This is primary, this is secondary. Okay, secondary makes enamine, primary makes imine. So what does this one make then? This is a secondary cyclic amine. So it's going to make an enamine as well. But where's the double bond going to be? Is it going to be in here, or is it going to be here? Well, it usually comes from the carbonyl, because remember, if you picture the nitrogen here, you need the elimination to occur here, right? So it's going to always be with the carbonyl, not with the amine, all right? So that's what it should look like over here. Now, if you're not really seeing it the way I'm describing it now, because I'm sort of just talking through it, I really recommend you stop and just sort of go through the mechanism until you do understand it on the level where you can talk through it, okay? Meaning, stop right now, do this mechanism so that you can see exactly how you get this. There should not be any guesswork to this at all. You should be able to use the mechanism to figure these out. That's the point of them, I think, is to understand it at that level. But after you do enough of these mechanisms, you're going to be at the point where you can just look at it and you know, okay? So that's ultimately what would be great if you could get to that level, okay? All right, but until then, just put in the time and just, work them out until you get it. All right, next one would be here I can picture that this is going to attack here, and then I have excess alcohol, so I'm just going to attack it twice. and get my acetal. Okay, again, you want to work through the mechanism to be sure that you understand that. This carbonyl oxygen ends up as water, and that's because I have acidic solution to help turn that into water. This one as well, carbonyl with an alcohol, same thing. I can attack the alcohol twice. I will get an acetal with the alcohols now as ethers. For this one, number 6, it's a little tricky. It's intramolecular. Within the same molecule, I have a carbonyl group and an alcohol group. So it's almost as if I had a separate alcohol, but it's on the same tethered. It's tethered in the molecule, so I'm going to attack it here. Usually an intramolecular reaction occurs when you have 5 or 6 membered rings because they are, it's not a lot of ring strain with those, right? So if one attacked 2, okay, then these electrons go up like that, then I'm going to end up with this. How did I get that exactly? Okay, so let's I like to number things so I understand them. 1 is the O. It's going to attack carbon 2. Carbon 2 ends up getting electrons up to here, and now it's an OH group. This will be 3, 4, 5, and 6. I have everything accounted for. At the very beginning, when I just saw this, I knew to draw a hexagon rather than a pentagon, for example, because I went 1, 2, 3, 4, 5, 6. I just counted. Okay, so I knew it was a 6-membered ring, including the oxygen. Okay, so that is technically a hemiacetal. If you look at this carbon, it's got an OH group and it's got an OR group, but the R group happens to be connected, okay, because it was intramolecular. So this is a hemiacetal. Again, it's sort of hard to see that, but a hemiacetal has an OH group and an OR group on a carbon. An acetal has 2 OR groups on a carbon. Okay. So good to know the difference. And a hydrate has an OH and an OH attached to a carbon. Okay, those are the ones you want to know. All right, so for this one, I have a hydrate. I have acid, but I don't have water. Okay, I don't have alcohol. I don't have anything. Okay, so what's going to happen here is probably, and this is favored with heat, is to drive off water. So I'm going to turn the hydrate back into the carbonyl. You've learned how to go from the carbonyl to the hydrate. So this is an application where we didn't go through it, but you should be able to do the opposite, where you take the hydrate and you go back to the carbonyl. Why don't we make that for homework? We sort of, not to turn in, but just for you to practice. How would you go from here to here? Show me the mechanism for that, because these are reversible reactions. But basically, I'm looking at the hydrate, and I'm not adding anything to it. I'm just eliminating with acid. Acid is a good dehydrator. It's good at losing water. So I'm going to make a carbonyl group. Okay. Next one is excess water and a carbonyl. This is the reverse of what we just did. So now we're making the hydrate. Okay. And again, excess water, that means water's attacking here. And then this turns into another OH group. Okay, and let's label this. This is called a hydrate. So start learning your vocabulary, because it might help you in explaining these to yourself or just expanding the way that you think about these things. All right, this one is an acetal. See the OR groups up here? OR, OR, where R is an ethyl. So this is an acetal. And when you have water, you can replace the OR group with OH, so you get the hydrate. Should be able to show a mechanism for that. Okay. All right, this one, you have the acetal, adding water, same thing as we did above. This is a hydrate. And finally, last one, we have, what the heck is this? It looks like an alien, right? Okay, what this is looks like a cute little bug, actually. This is an OR group, this is OR, but they happen to be attached to each other, that's all. So this is an acetal. Okay, so picture that these are sort of like R groups. And then with water, you replace that all with water, with OH groups. Okay, so these will get protonated, water will attack and let go of this, and then this will be one molecule, the ethylene glycol right here. All right, and so we're going from acetal to a hydrate by pushing it forward by adding lots of water. Okay, there you have it. Okay, so for practice then, go through these again. See if you can just predict what the products are correctly. If you have a hard time, go through the mechanism and let the mechanism help you figure that out.